Welcome to another episode of Code for Thought. And a Happy New Year to you all. And welcome to Season 7 of Code for Thought. And as of January 2024, this month, Code for Thought is exactly 3 years old and has published 100 episodes, all of which is made possible through you, the listener. So thank you for tuning in and supporting this show. And in this new season, you continue getting a new episode each Tuesday. And as of last year, there'll be a German language episode on the last Tuesday of each month. And in Season 7, I will also continue my collaboration with the Universe HPC project on bite-sized RSE with 6 more episodes until summer. At the core of bite-sized RSE is a short standalone training session with a focus on practical exercises. They're given online by different trainers and happen once a month. And for each of these sessions, there'll be a companion podcast episode published on Thursdays, usually the last Thursday of the month. So in short, there'll be plenty of content to get your teeth into, and I hope you'll find the material interesting. I'm certainly very excited about the lineup of guests and themes for this season. But I would also like to hear from you. Code for Thought is not meant to be a one-way street. So if you have ideas for interview partners or topics, if you have some feedback, or you want to be on the show yourself or host an episode, contact me on Slack, Mastadon, LinkedIn, or simply send me an email. You'll find the contact details in the episode notes. I want to kick off Season 7 with a subject many of us find important. What role does computing play in terms of energy consumption and greenhouse gas emissions? And what is it that we can do, we who write, maintain, and run software? This is no longer a fringe subject. The commitment to a net zero strategy affects all parts of society, and that of course includes computing in all its different aspects. As you will hear later in the interview, roughly 4% of all emissions are down to computing one way or the other. A number which is bound to go up as we see an increase in devices and also energy and compute-intensive services such as high-performance computing, data centers, cloud services, and so forth. It is also a very complex subject, and it covers the wide field from the production and creation of computing hardware and infrastructure to the disposal and waste of electronic devices. At the end of 2023, I talked to a number of different engineers and researchers who work in this area, and you'll hear from them during the season. My guests for this episode are Wim Vanderbauwhede from the University of Glasgow. Wim is spending a lot of time and effort in this area and is also the lead of the low carbon and sustainable computing activity at the university. My second guest is John Wernvik from the Datacentre in Sweden, from who you will hear briefly later. But first, let's hand over to Wim. Hello Wim, and welcome again to the show. We talked about Fortran the last time we spoke, which was quite good fun. But today I want to talk about energy consumption in computing. But before we do that, maybe you can quickly introduce yourself again.
Yes, I'm Wim Vanderbauwhede. I'm professor in computing science, and my focus at the moment is on low carbon and sustainable computing. This involves both the energy we use to run our computers and the energy we use to make them, and particularly the emissions resulting from that energy use.
That is exactly what we want to talk about today. Obviously, there is climate change happening, despite some people still denying it, surprisingly. And the question is, how much does computing contribute to it in its various different aspects? And I think there are 3 different aspects, 2 of which you already mentioned, which is the production of computers, so the manufacturing of it, then the running of it, and then the disposal of it.
Yes.
I guess we're not going to talk about the disposal today. So just to give us a flavor of how much energy is actually involved in production and running it, sort of, do you have some kind of figures, or do we have an understanding of what that is?
I don't have the energy figures. I mean, I have them somewhere, but in terms of emissions, the picture is a little bit more clear. So the estimates from a few years ago were that the whole ICT field contributes up to 4% to global CO2 or greenhouse gas emissions, not just CO2. The distinction is important because chip manufacturing uses some of the worst greenhouse gases that are not CO2. That's why it has a comparatively large footprint, because these gases do a lot more damage than CO2. But so, yeah, that's 4%. And that was a few years ago. And I think it might have gone up simply because of the current. Well, I hope it's a hype bubble with AI, but it might not be, because that requires a huge amount of compute, and therefore everything goes up, right? But that 4%, let's say, is split roughly 50-50 between use and manufacturing. For end user devices, it's dominated by manufacturing. So your mobile phone really doesn't use all that much
Mm.
energy for running, but it uses an awful lot of energy for production. And so you basically, the only way you can offset the climate cost of a mobile phone is by using it for much longer than we do now. It's one of the things I keep on reiterating, that end user devices should be used for way longer than we do now, and therefore we should change our practices to make that possible. It involves a lot of things because, in fact, we are not set up to support devices for 20 years, not on software and not on repairs.
I think
Or,
that's a
yeah.
very good point, actually, because I've been going through this actually quite recently. So I had a MacBook Pro bought in 2015, a machine that actually works quite nicely, but it doesn't work quite nicely with modern versions of the Mac OS for a number of reasons, because they changed the chipset and therefore sort of the software changes, etc., etc., etc. But they make you change things more frequently. And I think the
Yes.
same with mobile phones, where they stop supporting older devices at some stage, and
Yes.
therefore people feel obliged to buy new ones.
There's a bit of a positive trend there, to be fair, is that at least for the high end models, the support has now gotten longer, up to 6 years for some devices. It's a long way away from the 20 years that we would need, but I'll take it if it compares to 2 years before. But that's the main observation, that the reason why we obsolete our hardware is the software. Usually
Mm,
it's not because it breaks, it's because it's no longer supported. And supported means that the vendor can't be bothered, on purpose does not offer the software anymore for your older device. So they do that on purpose so that you would buy a new one. And that's because their current business models are such that they make more money by doing that. So
mm,
changing that business model is another thing we really need to think about. And it's possible, right? You could easily imagine that instead of buying new devices all the time, you would have, let's say, a lifelong maintenance contract. And then it's in the vendor's
mm.
interest not to have a device that lasts very long, because otherwise they have to give you a new one, right? So if it breaks, it costs them. If that would be the situation, then they would make money
Mm.
from making sure that things don't break. And it already exists for things like smart light bulbs and so on, but people really don't want to have to replace these things.
Yeah, indeed.
I'm now in a project at the moment at the proposal stage where we look at such things like, for example, heating as a service. So people have heating or cooling and climatization as a service. It's definitely in the interest of the company that puts your heat pump or your aircon in, that it breaks as little as possible, because otherwise it costs them. That is already a model that exists. I mean, it's in its infancy, but there are companies already out there. So we can see there is scope. It's just a matter of moving things in that direction a bit more, and
Mm.
that's through awareness raising, right? So,
But I think it's also quite important to highlight what you just said, that it's not just the hardware, it's also the software that we run on things, and
yeah, yeah.
that influences the energy consumption.
In fact, my whole point when people say, yeah, but the emissions come from the hardware, is that the hardware only exists to run the software.
Indeed.
Because if there was no software, there would be no point in having the hardware.
Indeed.
I mean, and that
Yeah.
goes for everything. It goes, in fact, for the whole internet infrastructure. It's all
Mm.
driven by the software that runs on it. And therefore, it's in the end, ultimately, it's the software that causes the emissions.
Yeah, and but for years we've been getting away with Moore's law, which says that the computing power increases and therefore we can throw more software at it, or more powerful software. Does that still hold though?
Well, Moore's law was an observation about the doubling of the number of transistors on the chip. And what has been happening is that people have been redefining this over the years so that it could still hold, because industry needs this kind of perpetuating trend. In short, the original Moore's law doesn't hold anymore. It stopped holding about 20 years ago when we moved to multi-core and then many-core. But of course, you can say, well, in terms of number of chips, they keep on growing, and the performance keeps on growing, but we have never been so good at actually using that potential because parallel programming is hard. And it's great from a commercial perspective to say, here you have an octo-core mobile phone. I really wonder how often these 8 threads are busy, right?
Indeed.
Because for a lot of activity, it's not needed. Anyway, that's a bit of a separate issue, I suppose. But the law that is important is what is known, I think, as Kumi's law, which is the observation that the energy efficiency also follow the logarithmic pattern. Because that's
Right.
actually more important. It means you double the compute and you at the same energy cost, roughly double every 1.5 years or something. And that has been going, although the slope has been decreasing, and we're really
Mm.
seeing that it's flattening out more. But that's really, from an emissions perspective, at use, that's the important part. And that's also what justifies people in, for example, supercomputers to buy a new one, because in a supercomputer, it's not the embodied carbon, the carbon of manufacturing that dominates, it's the carbon of use, because these machines are run in such a way that they maximize utilization. And therefore, when you upgrade those after, say, 4 to 6 years, you do get energy efficiency savings. And the supercomputer centers know that because, well, their cost is the energy cost. They are actually motivated in doing that. And that's what Kumi's law, again, it's an observation, right? But we see that this is what happened, and that's why we see it. It makes sense for high compute incentive jobs to upgrade hardware periodically. But it's coming to an end, and in any case, it will end because there is a fundamental physical limit on this. It's called Landauer's limit.
But you could explain that anyway, what that is.
Yes, Landauer's limit is saying that if your computation is not reversible, which means that, for example, if you have an AND gate and you apply 2 bits to it and you get 1 bit out, it's not possible to reconstruct the 2 initial bits that
Mhm.
went into it. So you've destroyed 1 bit of information, so your computation is not reversible. If you wanted to make it reversible, you would have to keep that other bit or information that is equivalent to it. And in CMOS, we don't do that, because if we did, it would be actually worse in terms of energy consumption. But nevertheless, it means CMOS is irreversible computing. It means we destroy information, and by destroying information, we increase entropy, and that puts an upper limit on how efficient we can get with our computation. So
Mm.
Kumi's law cannot hold infinitely because of Landauer's limit. Actually, that's been observed in the lab. It
Right.
used to be a conjecture, let's say, but it's actually been observed. People have measured the amount of energy it costs to destroy a bit. This means that sooner or later, and the projections basically say something like between 5 or 10 years from now, we hit Landauer's limit, and therefore, at that point, our efficiency gains really are gone.
All right, and that means also that the energy savings that we hope to achieve will be gone as well, and actually the consumption then will go up,
Well,
or the needs will go up.
at least
Is
in
that what you're saying
hardware,
then?
yeah.
Yeah.
That's why people like me say, yeah, but we can be so much smarter in software. And I'm not the only one. There's a great paper from MIT, I think, Room at the Top. So basically, long ago, Feynman gave this talk where he said there's plenty of room at the bottom, which was about using hardware tricks to make. That was before they had integrated circuits, right?
Yeah.
And so he was saying that we could, at low level, do a lot to speed up computation. So this paper plays on that and says there's plenty of room at the top, which means like we're so inefficient because we never had to be efficient, because Moore's law and Kumi's law, there was no point. We just wait 1.5 years and that's it, right? Why would
Yeah.
we exert ourselves to be super efficient? And therefore, the whole stack is super inefficient. Well, not it's really inefficient. There's a lot of gains to be made at the top. So we could keep on saving energy,
Mm.
runtime energy, that is, even when we hit the end of efficiency increases, because there's no point anymore than in upgrading the devices unless they would really break, be used for longer. And so we could actually still save a lot, I think. If you really think of what the problem is, it's not the technological side, right? It's the economic side. It's people finding new ways to make money by expending energy, and therefore by polluting, and because it does not cost them. Therefore, we could do all we can as engineers to make that also efficient as possible, but it doesn't stop, and it needs economic regulation, I think. Basically, it means that the externalities, in particular the greenhouse gas emissions, should be paid by the people who cause them, even if it's indirect. They couldn't make money anymore from things that pollute, if that was the case. And this is not a new idea. This is carbon tax or cap and trade. There are all these mechanisms. It's just that
Yeah.
they don't apply to the ICT industry at the moment. Cap and trade doesn't apply to that. So that's why OpenAI, for example, doesn't have to worry about their carbon footprint, because it doesn't, apart from the pure electricity cost, it doesn't really cost them anything to have unlimited growth in their business.
Yeah. I want to move on a little bit because there is a trend that we're seeing, and you mentioned that already with ChatGPT and OpenAI, etc., of using computing centers more. So it's kind of ironic, I find, because in the 50s and 60s, we had these big central computing powers and
Mainframes.
then the mainframes.
Yeah.
And with the punch cards, I'm getting a little bit nostalgic here. But anyway, we had that. And then sort of in the 1980s, the personal computers and the personal devices became, you don't need all these big machines anymore. You could run it basically at home. But we're kind of moving back into this era of big computing centers.
Mm.
Of course, the problem, as you already mentioned, is with the computing centers is they run a lot of energy because there's a lot of cooling involved, the energy that the devices consume, etc. So do you see that we have an increase in data centers, an increase in central computing powers, software as a service, etc., that
Yes.
shifts the energy balance a little bit? Is that something that you worry about?
I do. I mean, what they call a hyperscale data center or cloud is as efficient as it gets, because their main cost is their electricity bill once they've built it. So they have a really strong incentive to make sure that, for example, the overhead of cooling becomes very low. For example, they can run the whole thing on low voltage networks. They don't need transformers for every server and so on. And there's lots of efficiency gains there that they can make and that they do make. So it's not that cloud data centers are not efficient. It's just that because the expenditure of energy is hidden from the consumer, you are not aware essentially of the carbon footprint of your actions anymore.
Mhm.
Because your phone, you do something, it talks to the data center, the server does quite a lot of work, but it all goes really fast because all our stuff is super fast. And you are not aware that this required a huge amount of energy to do even just a simple thing. And so that's one aspect of it. The other aspect is that one of the problems with cloud data centers is that they, at least for the major customers, they have service level agreements that require them to provide, to be always on and actually always over dimensioned. And so
Mm.
they have a lot of servers that are only coming online when there is a peak demand.
Mm.
But the embodied carbon for those servers has been incurred, and also they are not completely off, of course, because that would take too long to spin them up. And so there is a large cost there purely because they have to provision for peak. And that is not the case with an individual machine in your local business, say, because you are better able to judge this. Because the problem with something like an Amazon cloud is that they can't really predict the workload at the moment when they build it. And that's when they have to provision. Also, they are very careful in not disclosing how much of the servers are not used. There is a reason for that, I think. But so that's kind of a
Mm.
hidden aspect of this, is that there is a lot of unused resource, most of the time unused resource in there that cost in terms of emissions. And of course, there is another aspect, is that because it's remote, you need the network infrastructure, and the
Yes.
network infrastructure consumes a huge amount of energy. Now, it's not the way people naively seem to think. You see that a lot, like people think that the energy consumption of the network is proportional to the amount of data that you send through it. And
Mhm.
it's not like that. Simplifying, the network is always on, and whether you send a large video through it or not, it makes no difference in energy consumption. I mean, it's not
Mm.
quite like that, but it's very close to that. But what happens is, if the demand for example, in particular video goes up, because the vendors have decided that we now need 8 HD, rather than 4 HD. Although the eye can't perceive this anymore, it still means the volume of video increases dramatically.
Mm.
And that means the infrastructure needs to be increased in capacity in steps. And each of those steps consumes a huge amount of energy to put in and then operate that infrastructure. So you get basically a stepwise increase in emissions, and the emissions of the core network are very large. I
So
mean,
in what way and why are they very large?
well, with the core, I mean everything that is not the Wi-Fi router in your house. I talk both about the wired and the wireless network.
Hmm.
Well, it takes a lot of power to power 5G, 4G, 3G masts concurrently, and they are not very dynamic, so they don't really go into sleep easily.
Okay. Mm.
And the core network, the problem there is that the actual for a wired network, the actual core is optical. It's actually the power per bit is very low, but the let's call it the edge for convenience is still doing an optical to electrical conversion, and those routers tend to be very power hungry.
Okay, so
Um,
we're talking about so that you have an optical cable network, like for instance where I live. So we have an optical cable to the cabinet, and then you need to convert it into an electrical signal because there's a copper wire going into my house.
Yes,
Is that
and
what
in
you're
many
talking about?
places, I mean, now we're rolling out fiber to the home or fiber to the
Yeah,
endpoint. I mean, fiber to the cabinet is not a big deal because the copper wire is only going to be a few hundred meters long.
yeah.
But at the moment, the more common scenario is where you have a few miles of copper doing the final distribution. Also, it is a fact that a lot of the routers are actually not fully optical routers. Right? They
Mm.
do an optoelectronic conversion, route electronically, and then back to a electro-optic conversion because it's quite hard to do optical packet switching at IP level. And so these things therefore consume a lot of power. Um,
So what we're getting in this conversation really is the complexity of the
yes.
kind of things that we need to consider when it comes to energy
Mm,
consumption. So we have the
yes.
production of the device, we have the running of the machines, which then also is where software comes
Mm,
in terms of its lifespan of the machines as well as the energy consumptions of the machine. Then we have the data centers, and then we
mm,
have the network that connects the data centers or the
yes.
computers with each other.
And the network, even there, you get the software issue, at least if we call the protocol software, let's say. So the
Mm,
data structure of how the data is encapsulated and the protocol that deals with how you transmit it. For example, TCP is notoriously bad at dealing with congestion. It backs off in a very poor way. Backs off meaning that when the transmission didn't succeed, it has this kind of algorithm that makes it wait for a while and then try again and so on. And actually, a lot of the protocol, because it wasn't really designed for the volumes that we now see, is inefficient at protocol level. Like, for example, also, if you think of things like massive video broadcasts, at the moment they are mostly broadcast by unicast, meaning that it's not really broadcast, it's a unique connection between everyone's viewpoint and the servers.
which is
And
what unicast means.
yes, and if we could do true multicast, which we can, but it's not widely deployed, that saves a lot of energy purely because of not having to duplicate the sessions. You see, even at the network level, it's actually still a software problem.
Exactly, and I think that's a nice finish for our conversation. So, because there is actually, as software engineers, who we are, or at least a number of us, what is it that we can do to actually help saving energy? So, you mentioned there's room at the top, and is there room in software as well where we can do things better?
Yes, yes. Like, for example, I've been looking at the inefficiencies in software, scientific software, at what level they are. And it's quite amazing at how many levels there are inefficiencies that we could address. And actually, I was a member of the project to look at how we could go to net zero for the UK research infrastructure, digital research infrastructure. And the main advice, and you'll love this, of course, is we need more research software engineers. We call them green software engineers because that's really
Okay.
what we need. We need the
Yeah.
expertise to make sure that our software is as green as possible. And this is not just how you write the code, it's also the practices of setting up, developing, and setting up experiments. Like, for example, a very stupid thing is that a lot of people don't do proper testing and then they
Mm,
deploy their code and then, damn, there was a bug in it. And then they have
mm.
to rerun their experiment on a supercomputer, right?
Right. Yeah.
Because typically the way the grants work is you need to show some scalability to get in, but once
Yeah.
you're in, you're not really monitored, or certainly not. It doesn't cost you
Mm.
to rerun things apart from your own time. So the practices of like there is code auditing and unit testing and integration outside of proper software engineering communities, that doesn't really exist. That's just one thing. And then you have the code architecture, which software engineers are better at than scientists. And then there is compilation, because it turns out that I haven't finished this, but we've been looking at the effect of purely compiler flags and compiler choice on performance. And it's quite eye opening how much opportunity we miss by not using the correct
Compiler
settings,
flags.
even though, yeah. But again, it requires expertise. It all goes back, at least from the research perspective, narrowly focusing on that. It goes back to we need more research software engineers. That would solve everything. I mean, not everything. I mean,
It could help to solve everything. So I'm not
no, it would make a massive
Yeah.
difference, because on the hardware side, the operators of the supercomputers, they are already very aware, and they are actually pretty good at saving energy because it's in their best interest. So that side is already covered in a way. The side that is not covered is all the little clusters that we have all over the place. That's a different issue,
And
because
how
that
they're
can
being
be
used.
addressed very much by like a concordat between the research councils and universities and so on. But so yeah, a lot of this is actually kind of transferable outside of research, in the sense that there is a lot of software being made and used outside of software companies. And so expertise to do things better is really very much needed. And training as a result, that's the main thing that we can do as on the software side.
Okay. Well, thank you very much, Wim. That was a very interesting discussion.
Yes.
And good luck and all the best. Wim mentioned a number of papers for which you'll find the links in the episode notes. For instance, the article on There's Room at the Top. There are also other links to Wim's online articles on the same subject you may find interesting. In our discussion, Wim and I touched already on data centers and their energy consumption. Data centers have come more into focus in recent times, and that's hardly surprising given the increase in cloud services, central data and computing resources. Data centers run on a substantial amount of energy and resources, so it's right to shine a light on it. For instance, I remember a report from September 2023 where a high-performance computing center in Iowa, the US, used by Microsoft, gobbled up huge amounts of water to the detriment of the local community. But, as Wim and I discussed, data center operators have an interest to keep the costs down for energy and resource consumption, and some effort has gone into optimizing that. Which brings me to my second guest in this episode, John Wernvik. John works at the Eco Data Center in Sweden, and in our brief conversation, John explains some of the steps they take in designing and running more sustainable centers. So here's John. Hello, John. Thanks very much for meeting me today to talk about data centers and their energy consumption. But perhaps you can quickly introduce yourself.
Yeah, sure. Thank you for having me. John Wernvik, I'm Chief Marketing Officer at Eco Data Center. So I work, of course, a lot with marketing, but also a lot with sustainability related topics.
So we're talking about the energy consumptions of data centers. Give us a feel for how much energy a data center consumes. I know it's a bit of a difficult question to answer because it depends on the size of the data center, but just sort of what is the order of magnitude that we're dealing with here?
Well, there's somewhat of a black spot right now, but what a lot of people are agreeing on is now with the tremendous explosion of AI services, the energy consumption in data centers will be a huge challenge for society as a whole. I mean, there was a scientist from Netherlands that published just last week a report on if you take NVIDIA's GPU orders for the next coming 3 years and take the energy consumption needed to supply that, it would equal the total amount of energy produced in the Netherlands. So, I mean, of course, it will be a huge amount of power needed to support this new generation of GPUs and high performance computing clusters.
And I think on your website, it says that you don't engage with cryptocurrencies.
Yes.
Is that correct? Because their energy consumption is too high, or what was the reason for that?
Yeah, because we see that there are, of course, good things about cryptocurrencies, but for the moment being and the energy consumption that they take from other applications, when now power becoming a scarce resource globally in the energy transition, we feel that energy can be used for better purposes than that. Then I know the crypto community is doing a lot of things addressing the power consumption, but as for the time being, we feel that the sustainable infrastructure we help provide is much better served for other types of applications and purposes.
So it brings us to how you are trying to help making data centers more sustainable, because I think you have sites in Scandinavian countries, in Sweden, which is where you're based. But perhaps you can tell us a little bit about more how data centers can be more sustainable and what it is that you're doing there.
Yeah, absolutely. First, I would say it has a lot to do also on where you locate the data center. We are very fortunate in Sweden having a tremendous amount of renewable energy and having a very favorable climate for data centers. But then also that, of course, is not enough. We also try very hard into create a circular system where we can use the energy consumed at the data center twice, reusing it. Now we currently reuse it for district heating, and we reuse it to help produce wooden pellets or biofuel. So then we get a second purpose for the energy we consume, which we think is quite neat and something we will develop a lot more applications going forward. So I would say that that's one aspect of it. And then there's other aspects as well. We build in wood to lower the embedded emissions of materials used to build the data centers. A lot of other build data centers out of concrete and steel, for instance. So we try to think of it in everything we do. How do we decrease the CO2 emissions we create?
Data center, you're talking about the circular reuse of resources. My understanding is that a lot of the times cooling is provided through water cooling, and that, of course, means that water needs to be supplied in order to facilitate the cooling. And there was a report this year that some of the resources of water centers, I believe in the US, use a huge amount of water that is then impacting the community. So how you're dealing with that?
There's also one of the huge benefits of being in Sweden. I mean, here, water is not a scarce resource at all. We have a bunch of domestic lakes, rivers, etc. And it rains a lot of time during the year. And then when the snow comes, we can melt the snow and use that water instead. So for us, we feel that the water topic is, of course, will be even larger if you look at warmer countries in Southern Europe, for instance, and in the US. But here we have it in abundance. And I mean, as long as we don't use drinking water and using the day water, in Sweden, that's never going to become a scarce resource.
Of course, not every data center is located in a favorable location such as Sweden. So my final question would be, what kind of recommendations would you have for data centers that are located, say, where the temperatures are a little bit different? What is it that we can do to make data centers more sustainable?
Of course, a lot of data also need to be in warmer climates and warmer countries. I think as digital and compute is so integrated in society now, I think we need to have a much broader discussion on actually where we put the data from a global perspective and put the digital resources where they don't harm the climate and where it makes sense. Then I'm, of course, a bit biased in that reasoning, but I think that there will be a time now for the coming years that will increase the not perception, but I really think that the digital consumption of everyone's lives and the digital impact from an emission perspective will be at the very center of the discussion.
Okay, thanks very much, John, for this brief interview, and I wish you all the best for the future.
Yeah, thank you.
I got to be honest with you, when I started working on this episode, I realized what a huge area this is, and I feel I barely scratched at the surface. I do hope, however, that I've given you some food for thought on the environmental impact computing has. And later on in this season, you will hear from Loic Lanelong from Jesus College in Cambridge, who, together with colleagues, has been working on tools to estimate the costs of computing and algorithms. In the meantime, let's take to heart what Wim recommends. We need more software engineers and research, and let's avoid waste by testing our code properly. In the next episode, you'll be hearing from Veronika Czeplutschina, Associate Professor in Copenhagen, and her work on the use of artificial intelligence and machine learning in medicine. And with that, happy 2024 and see you next time. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.